Yeah. Okay. All right. Welcome to, is it week 9 or 10? One of them. I think it's week 10 or 9. Probably 10. We'll change this post production. So we've learned a lot of classic data science techniques. Obviously, we can't cover all of it, right? There's too much to learn, but my goal is to make you well versed in a good chunk of these ideas so you can at least work in a data science environment or just improve yourself. Okay. So we learn how to train a bunch of different types of model. We learned some core ideas on how we're going to use text. Today, we are detouring a little bit. So you've seen all of these really big models that have been created from early 2000 GPTs and all these like little LLMs and big LLMs and transformers and multimodal stuff. The general idea, and I'll explain what this is that we can reuse the things that these models learn for new tasks without having to train with new data. So let's learn a little bit how this is possible. Again, just the core idea. Okay. So I showed you how we can turn text into vectors, right? Showed you bag of words, you count TF-IDF, things that are prevalent in every document become less important, right? And then each dimension in your document is a whole, is like one word in the vocabulary. So you can build really large vectors from your documents. And then a message becomes a list of counts. So essentially, this is what we did, right? We had the raw text, we tokenized it within using some method, we counted the words for a document, and then we used the TF-IDF method to weight it, and we created this sparse vector. Sparse vector means it has everything is 0 mostly, and then there's a few values. And then we use it to cluster, right? So in A3, assignment 3, and then yesterday we clustered businesses using these numeric features. We can do the same thing for text, and we saw how that's possible. We can treat each TF-IDF feature vector a point in a high dimensional space. We can run k-means on it, dbScan on it, PCA on it. All of these apply, right? So can we just use TF-IDF or some metric like this for everything? Is this useful? The general idea is no, right? Because the stream is fire and the broadcast is lit are two different vectors, right? But these shared words carry little weight. They show up everywhere. Meaningful words don't overlap at all, right? And the cosine similarity between two is very little. And I'll show you what cosine similarity is, right? So if we just use these two vectors, we're going to say, oh, these two sentences are not similar. But when you read it, you know that these two are about the same thing, right? You even know that it's probably from the same type of people. Lit and fire are not words that I use. You might guess that this is like a Gen Z thing, right? There's a lot of information in this context. So just using these words is not good. Generally, from a data science perspective, these sparse vectors are huge, mostly empty, one dimension per vocabulary. It's exact match only. There is no sense of synonyms, right? Meaning isn't represented, only word identity, right? So what if we can create these vectors that have a better sense of word meaning, better semantic sense? This is the idea behind word embeddings, right? So you train a model a large amounts of data. It learns the context, learns the words, where they come from, how they do things, right? And it gives you a denser vector. Denser because it's less sparse. still could be sparse, right? So the idea is that we are learning through a learning process. If you take the AI course, you do more of this. We're here putting a data scientist hat, right? So if a sparse vector looks like this, a dense vector looks like this. It has fewer dimensions. Let's say a sparse vector has 1 million dimensions, the input. It could turn it to 10,000. It becomes denser. It carries more information. There's more signal, and this is learned. So a denser, lower dimensional vector representing a word, sentence, or document. It's learned from data, and it's not counted like TF-IDF. TF-IDF could be the input to the model, and you can use that to learn what the contexts are. So the idea that similar meaning, vectors that land closer together. And vectors are like, if you think in 2D, and if you remember your linear algebra, this is one word, this is another word, and from the origin, that's the first word vector, and the second word vector is this, basically. And we'll learn how this works. So the idea is this, if you had only 2 dimensions. But we treat everything in vectors, and we can figure out how things land closer to each other. And with this idea, we can do a lot of things, a lot of cool things as a data scientist. So this idea is that you can create this map of meaning, right? So you can basically have words like rabbit, dog, and cat. Now you know these are animals. You cluster them close to each other. Angry, joyful, these are emotions, right? You can think of foods or music genres. They land closer to each other. The other thing that you can use with embeddings is that they not only group similar things, you can encode relationship as consistent directions in space. So let's think of the words man and woman, okay? And then have the word king. So this is a concept that's taken from word2vec. So if you both of these have a vector, right? So if you get the difference between king and man, you get a direction from man to king, okay? And then if you add the same direction to woman, you get to queen. You get relationships between words. It's basically linear algebra. It allows you to do interesting stuff. You land near queen, right? Let's take another example. Kendrick Lamar and Drake. Kendrick and Drake. USA minus Kendrick plus Drake probably land somewhere in Canada. Okay? Relationships between words. This is the idea that the subtracting of vector and just doing things with it is one of the ideas of just how you can use these embeddings. Think about relationship, figure out how to do things. That's the intuition behind it. So the space captures a relationship, then we can add and subtract meaning, not just measure it. Okay? So the catch was from the example I gave you that these were from static word embeddings like word2vec and glove. Look it up on there are libraries that can build it for you. These are pre-trained on a lot of words, give you word vectors, right? These are one fixed word vector per word. For example, bank gets exactly one vector. Riverbank or bank account would not be different. But we have better ways now to create different vectors based on context. So now, where do these embeddings come from? Let's think about contextual embeddings. So we talked about one fixed vector per word, right? Today, models that actually read the sentence around the word, right? These come from pre-trained models, transformers, large language models. They're trained on large amounts of data, and then you can create those embeddings, right? You can create word embeddings, one vector per word or token, or you can create text embedding or document embedding. One vector for the whole sentence, message or document. the idea is different, the scale is different, and both matter for what's coming next, right? So the word embedding, if this gets this vector, the sentence embedding is a vector for all of them. A lot of this, what I'm about to show you, search, clustering, it happens in the sentence embedding level. So where do these come from? Pre-trained models, you train them once, and then you get them, right? We don't train it ourselves, we just reuse it. We call this transfer learning. Not one idea of transfer learning is using a model that's pre-trained for something else. Essentially, if you just take GPT and use it for some task, it's called transfer learning. You're transferring the knowledge from a broader task to a more specific task. So BERT, for example, generally was one of the first transformers. All of this ChatGPT stuff, I think, started from this idea. It was trained by playing fill in the blank on billions of sentences. So it reads the whole sentence at once, at both directions. It's good at understanding text, but it's not built to generate it. So what it does, it's, let's say it looks at this empty one. It's a classification algorithm, or basically learns what this word should be, the word in this context. So it gets the context from before and after and helps fill it, right? So it gives you a dense vector that's context aware. GPT gets the next word. It's what we use a lot of times these days. Left or right only. It's designed to generate text, right? So it looks at all of these words in this context, actually a really large context. When they say 1 million contexts, or all of these companies are fighting over context size, that's the idea. It goes back to a bunch of words, and it can use that information to predict the next words. Right? It gets you 10 vector, and it can keep generating new stuff. We have another model, it's multimodal, CLIP. It was trained on image and caption pairs. So what it learns, it puts images and text into the same vector space. So a picture of a dog and the word dog end up close together, right? So this is the idea. And all of these new multimodal models, the idea behind them, the intuition behind them is the same thing. So you take images and text that are paired with each other, you create a shared vector space. And newer LLMs build on the same two ideas. They read text, predict, and understand it. Most of them offer an embedding API, so you can send text, get a vector back. You can also use libraries like Hugging Face, which we're going to use on Monday to use these embeddings. So let's learn some of the things we can do with these embeddings, okay? We can look at semantic similarity, but how do we measure close? Embeddings put similar meanings near each other, but near needs a precise definition. We have two candidates: distance, how far these two are, and direction. Which way do they point? For embeddings, for getting semantic similarity, the direction turns to matter more, right? Why? Because we might have a short doc about an anime and a longer doc about an anime. They are very similar. The length doesn't matter, just the idea behind it, right? What matters is that whether these two vectors align or not, whether the angle between these two vectors is close to 0 or not. Okay? So that's why we use cosine similarity. We take these two vectors, calculate essentially the cosine of the angle. If it's 1, then it means they're very similar. So again, measure the angles between two vectors and ignore their length. Small angle vectors point the same way, it's high similarity. Large angle vectors point different ways, low similarity. Okay? So these two vectors are very similar, somewhat similar. These are unrelated. You can produce the cosine like this. It is a dot product divided by, I can't use these terms in English. Just remember what these are. The math I've learned is in Farsi, and I'm too tired today. But yes, that's what you can create it. Yeah, it's a dot product over the products of length. The length cancel off the magnitude, only direction survives. To read cosine values, it ranges from -1 to 1, 1 pointing the same direction, 0 unrelated, -1 pointing to opposite directions. In practice, most real embeddings comparisons you'll see land somewhere between 0 and 1. You can't really map this, it's more difficult. Okay, now you might have heard of RAG, retrieval-augmented generation. The idea is that models hallucinate things that are not true. That's the reality of the world we live in. A lot of y'all have used AI to give you answers and might have been the issue, right? So we use this for searching. You can do keyword search, find documents containing the exact word you type, right? But semantic search finds documents with the closest meaning, even with different words. Essentially nearest neighbors in embedding space. So if you have this space, you can find the n closest or most similar documents. So that's one of the ways we use embeddings. Is a language model only knows what is saw during training. We have new data. It doesn't know your private documents or anything after training cutoff, right? But you want to do stuff with it. And then when it doesn't know, it sometimes guesses confidently instead of saying so. It has no notion of knowledge, right? So we use RAG. We just do what? We say before answering is we hand it actual relevant text to read. How do we get the actual relevant text? We embed the question into the same space that the document, that the model embeds everything else, right? So we embed the question, then we have a document, we have embed all of the documents, compare what cosine similarity, and then we retrieve the top K matches, and then give the retrieved text to the prompt, and then ask LLM to generate that. This is the pipeline. It can get more complicated. There's flavors to it. The idea behind it is this. So without it, answers from memory alone can be outdated, generic. With it, its answers are grounded in actual texts that are retrieved, and then you can use that. So you're not changing the model, you're giving it new context. So this is the same idea behind chat with your own data tools. It's really useful for DS, and it's pretty simple. You can really build something with this in a lot of different contexts. Like you can go to any company, they have problems that RAG or something like RAG can solve, and they don't know. Like they want to pay millions of dollars to ChatGPT to do it, but you can do it for them. Doesn't really require training. You just use embeddings, a search, and a prompt. Okay. We might build a simple RAG system with Streamlit next Monday if you all want. Another thing we can do is topic modeling. I've shown you clustering, but what is topic modeling? So you can give it a pile of document, we get back groups or clusters, and a description of what each group is about. It's fully unsupervised, no labels needed. You can interpret the output. There are a lot of different methods, but one of them is this. Get all the documents, embed each of them, cluster it like what we did, we're going to do in assignment 3, and then extract top keywords somehow from the cluster, and those are the words that represent the cluster. Or just give the cluster to an LLM and ask it to describe what this is for you. Or use other types of method. So you create topic labels, and that is the label of your cluster, so you know what it is about. So we have really nothing new here. We know how to do this. a lot of times it's really good if you get clever with the things you're learning in terms of data science. You mix and match, compose, and do something. So there's like a library called BERTopic that, let's look at it. I want to show you. It's like a whole library that does this, but the algorithm. What does it do? Can I make this not? Yeah. So you take sentence BERT, you reduce the dimensionality, you cluster it, you tokenize the output of the clusters, you use some weighting scheme, the TF-IDF that I showed you, and you get the best outcomes out of there. It's really simple. It's an interesting idea. So I've shown you HTTP scan, I've shown you UMAP, shown you sentence BERT, and you can replace any of these as long as you have embeddings. You can do so, like for employee surveys, for understanding social media data, for using this for, there's a method called topic guided thematic analysis. Let's say you run a survey on thousands of people and they've all given you qualitative data. How might you ask, do thematic analysis on a subset of them? You can do topic modeling and then use those topic to read samples yourself and add meaning to it. So sample from the data in a smart way. Okay? So again, pilot documents, cluster them, and then give them labels based on what they're close. This is powerful because solve the exact problem you have in A3. Okay, but what is this cluster? And no one had to really read the document and embed labels by hand, although that is sometimes needed. You can use it on any collection of text, reviews, tickets, chat logs, papers. And if you get clever, you can do this on images as well. So remember I showed you clip, it jointly embeds, right? You can do the same thing, tricks on images. So you can embed a folder of images with clip, cluster them. These are the ones that are visually similar. Conceptually similar images land together, basically. And because words live in the same space, you can find the closest word to each cluster center. We've already done the cluster profiles. The reason I told you the averages, because you can use that to do clever things, right? So you can give it 10,000 words and say, okay, what 10 words out of these 10,000 represent the center of this image? That those words are closest. So you're labeling clusters of images. You're not really training, you're not manually tagging them. So the idea is that, hey, these are the words that are similar to each of these clusters. So that was part 2 of the clever things you could do with embedding. Third is classification without much training data. So now with all these large, huge language models that we have, we can use them to classify things, right? So we looked at similarity, we looked at unsupervised. Now let's look at classification. So the old way that we taught you is collect a lot of labeled examples, hundreds and thousands, train a model, like the classifiers you've already built. And then generally these work for the task you train it on. Classify abusive versus not. These can be really efficient, really powerful models. But what if you don't have hundreds of examples? So we can have a zero labeled classification technique. So a similar idea to topic labeling, just aimed at a fixed categories instead of open discovery, right? So embed the message, embed the candidate labels, see which one is closer. That becomes your label. So you're not training, you're just embedding and then using Cosine Similarity, right? So message 1, get out of here. Nobody wants you in this chat. Clean, abusive. It's which one is closer? Or you can give it an example of an abusive message, an example of a clean message, and then you can get the one that's closest. And then you predict. This is called zero-shot classification. A second way of doing zero shot is just use the prompt. It's the same. It's going to be embedded. The prompt is going to be embedded in the model, and the output is going to be, so you're basically doing the same thing because the model, it goes through the layers of the model. So if you say, hey, is this message abusive or clean? You're essentially doing the same thing. You're not doing getting embeddings and similarity math. You're relying on the model to do this. Embedding based, prompting based. This is really powerful. A lot of these agentic systems use this method. You can say in the prompt, you say, if you really want to use this tool, if you figure that you need to use this tool, that's a prompting zero shot classifier. It can use the tool and do something for you. So the ideas that we're learning keep stacking up to the most modern technologies that you're using. Few shot is another idea. You can guess. You just give it a couple of examples. Still no training, no gradient updates. The example just lives in the prompt. So for embeddings, you have 10 examples, take the averages of them. 10 examples for clean and abusive, take the averages of them. You have a new message. Is it closer to that center or that center? You do that, right? Or usually you just say, hey, classify the message as abusive or clean. These are examples. Please mute your mic. Everyone can hear you breathing. Is this abusive or is this clean? The examples don't change the model weights. They just show that abusive and clean mean here. So you're altering the output. So zero shot, zero labeled, few shot, a handful of labeled, supervised, hundreds of thousands of example. Model is actually trained. And again, there are things in between. We can fine tune. So zero shot, few shot is one. I just showed you one of the examples of few shot, but you can use few shot to train a model. Let's say you have a model on figuring out faces, and you can show it 100 examples of angry and happy faces because it already knows faces, but with those 100, it might learn the difference between happy and angry and be able to predict happy and angry. So that's also few shot. So if you don't have labeled data set, you can still get working classifier today. All the metrics that you've learned, they work here. So you can calculate precision, recall, etc. You can prototype things. You can create agents. You can do all sorts of stuff. And again, this is directly used in your final project, which is going to be out tonight or tomorrow morning. I'm still working on it. So recap, 3 use of embedding, similarity, topic modeling, classification. Look them up. These are really good ideas for data scientists to know. I'm teaching you a toolkit of different sort of hammers that you can use to work with data. And we're going to work on these in the lab. We're going to learn how to use some of these simple techniques with a new library that you haven't used called Hugging Face. And we'll see what we can do. Any questions? How many of you are here? So let's stop recording. I'm done. Okay. Okay. So let me stop recording.